All right, so 54 balls, each with a unique number on them, 1 through 54, and 6 of them are chosen. And you're supposed to guess in advance the 6 numbers, right? This is a common lottery scheme in the States. I don't know about where you guys come from. So we're trying to figure out the chances that we get, 1, 2, 3, 4, 5, or 6 of these things right. And I'll start out by just computing the number of outcomes in the sample space. How many different results are possible? Okay, it says specifically that the order doesn't matter. It says something about in any order. So we get a clue there that we should use combinations to count this stuff, not permutations. Okay, so out of 54, they're choosing 6. So that's just 54C6. 25,827,165. Wow, that's a lot. So the chances that you get all 6 correct. Well, how many ways are there to get all 6 correct? Because remember, the fundamental probability principle is to divide the number of events in your outcome, the number of outcomes in your event divided by the number of outcomes in the sample space. Well, there's only one way to get all 6. If you want, you can check, but 6C6 is 1. And it makes sense. There should only be one way to get all 6 numbers. So the probability of getting all 6 correct is just 6C6, which is 1, over 54C6 comes out to be 0.0000004. Not very likely. 4 in 100 million. What about 5 of the 6? Well, this is a little bit confusing, but it turns out to be 6C5. That counts the number of ways we can get 5 of the 6 balls correct, times 48C1. What does that count? Think about it for a second. That counts the number of ways that we can get one ball wrong. 48 is the number of balls left over after the 6 balls that are the right number are already taken out of it. Okay, so we're counting the number of ways to get 5 of the balls correct and multiplying that by the number of ways to get one of them incorrect. Because if we're going to get exactly 5 correct, we also have to get exactly 1 wrong. And this second part, counting up the ways to get that last one wrong, turns out to be kind of an important piece. Alright, so the numerator, we're counting the ways that we can get 5 correct, and the denominator is still the same, that 25 million ways that we can choose 6 balls, period. So we divide them to get our result, which turns out to be also pretty small, but significantly larger than getting all 6 correct, 0.000011. Alright, well if that made sense, then the rest of it should be easy. The chances of getting 4 correct are going to be 6C4 times 48C2. You see that the numbers after the C's in the numerator add to 6, because we still have to choose 6 balls total, right? 4 of them are correct in this case, and 2 of them are incorrect. And the denominator stays the same throughout, 54C6, the number of possible ways to choose 6 of 54 balls. Okay, this one's slightly bigger, 0.000655. And once again, for 3 balls correct, 6C3 times 48C3 over 54C6. So if you do a couple problems like this, you get really good at finding how to do NPR and NCR on your calculator. Maybe now is a good time to pause and just mention how to do that. For the TIs, you're going to probably press Math, and then use the arrow key to move over to probability, which is probably represented as PRB. And there you should see a menu which contains things like the exclamation mark for factorial, as well as NPR and NCR. If your calculator is different, you need to figure out how to use it to calculate these things soon. If you can't, then you might want to consider borrowing a TI from Ms. Sonia and using that on the next test or quiz. So try to do that now for P3. Try to use your calculator to calculate 6C3 times 48C3 divided by 54C6. Should get 0.013394, is it? Yeah, so getting a little over 1% now. Alright, continuing on, the chances of getting 2 balls correct would be 6C2 times 48C4 over 54C6. Try with the calc and see if you can get 11.3% like I did. And then, of course, the chances go up a lot after that. Just getting 1 right is pretty likely. turns out to be nearly 40%. And getting none, 6C0 is not really necessary. That's just 1. There's only one way to choose none of 6 things. But if you put it in there, it just kind of fits. Times 48C6, we have to count up the number of ways to get 6 wrong out of 48 wrong choices. Divided by 54C6, almost 50%. Just a simpler example to illustrate why we do bother to count the non-matches, the wrong numbers. Let's say we have an example where there's just 3 numbers from 0 through 9. Let's say the 3 magic numbers are 5, 1, and 9. Suppose you match 2 of them. You get a 5 and a 1. How many ways are there to do that? Well, there are 7. You could get 510, 512, 513, etc. Okay, so it's important to realize that there are many ways to get something partially right and partially wrong. I hope that helps you to see why we have to count the number of wrong parts as well. In fact, the reason why the probabilities go up so dramatically and get near 50% at the end is entirely due to the fact that we're counting many wrong possibilities. Okay, that's why these things become so probable. Alright guys, this is hard and I want you to do a lot of examples here, including many even ones. So I'm probably going to have to send you the answers to those next week, or the end of this week. But please work on this. Don't wait until the end of the week to do it. It's going to take some time. Good luck. Kolpak out.